All right, I think we're good to go.
Okay, class, I'm done with you. As you want to finish the speaker because I didn't want to do another hour today, but please give your full attention to our industry partner, Plan Wisely.
Yep.
So let's have another class.
Fantastic. Thanks so much for having us. So my name's Javan. I'm a lead software engineer for PlanWisely. And I'm here with Lyndon, who's a here engineering manager, and Mitchell Holt, who rather confusingly for the Zoom, this is his account, so we could get in. So former tutor here. And so we've had the great pleasure with working with some students and former tutors of this very course. And so very excited to be here. And Paul's kindly invited us to give a bit of a industry presentation. So let's get into it. Okay. So a little bit of a trick question to start. What language is this? Is there anything that you can recognize? Stuff that looks familiar, stuff that looks a bit weird? Yeah, it kind of looks a bit Haskell-ish, yeah? Yeah. It's a trick question. No, we made this. Yeah. Pretty awesome. Yeah. So, I mean, now that you know that it's completely foreign, what are some things that you can recognize in it? Yeah, you got some types. Yeah. Where? Where's the where? I can't see the where. Oh, yeah. Where? Nice. Good. That's what we like to see. Yeah. Oh, yeah. They're not quite guards. It's kind of like a weird sum type thing. Yeah, but that's cool. You've never seen this before. Anything that you think is weird? Like what shouldn't be in a functional programming language? It starts with V. If anything else is fine. Yeah. var? Yeah, that's super weird. Yeah, why is that even there? All right. Well, yeah, we should probably using null or something. That's fine. Okay, cool. So we're going to talk a little bit about what planwisely is, what on earth motivated us to build a full programming language, domain specific, it's not really full. And then what the problem is that it solves, building our solution, and kind of how it went. So we should be about half an hour worth of content and ask questions through it. I'll try and be a bit interactive, and then we'll have some time for questions at the end. Let's give it a go. All right, so planwisely is a mapping tool for planners to understand places and the people who live there. That's kind of what it is. This is the marketing jargon that usually goes on these things. Here are some of our customers. So we work with government mainly, and also some private sector that have lots of shops to figure out where to put, and also kind of commercial real estate. That's a fun one as well. But what actually is planning? So essentially, like the easiest way to think about it is it's organizations figuring out what they need to invest in. And so for us, this means particularly places. So that could be a commercial place like shops, residential, where you're going to put a new apartment complex, parks and open space. And then kind of at a meta level, how do you get between those places? So transport infrastructure. So PlanWise is a part of Featurelistic Consulting, which is a strategic transport modeling consultancy. So they try and figure out, if you do this, how much will transport flows change? And so we work with public transport, active transport. It's a fancy word for walking and cycling, and roads. And then I guess the last category here is just going wrong. So what happens when there's natural disasters and some parts of the transport network are influenced? And yeah, if there's critical infrastructure that's cut off or missing or broken, it's good to know where those things are. So what does that look like in PlanWisely? So I've got a couple of screenshots here. Oh yeah, I am screaming the right check. Okay. So we've got at the bottom corner, land use designation. So this is Springwood, which was in the last 10 years or so massively developed. And so you can see the old planning scheme overlaid on the top, and then, this minutiae of housing. In the middle, we've got some jobs by industry. So this is a map colored by the number of jobs in each of those statistical areas around the Perth CBD. Those are retail jobs. At the top, we've got how people travel to work, also around Perth. And so that's also got the rail network overlaid. And so you can see pretty clearly that people are more likely to use public transport when they live near a train. Kind of pretty straightforward insights. But what I find fascinating about that one is that, still 75% of people use a vehicle. That's the purple part of the pie chart. So, kind of lame. All right. In the top right, we've got points of interest and relative activity, which is kind of saying that near where there's places that people want to go, people go there. I know, lots of that's big brain right there. Uh, what's kind of interesting though is you can see the activity tailing off as you go further to the left. So, that must just be residential or people's houses or something, and there's not that many people there. The last one, cannibalization analysis, fun name. So this is looking at, so each of those purple blobs is a how far you can get from that point in a fixed amount of time. So it's kind of a network aware as the crow flies. And what our customers use that for is trying to figure out, okay, if we put an extra shop, so maybe it's that middle one that's got a lot of purple overlap, they'd realize, oh, you know what? All we're doing is stealing our own competition. We can reduce our costs, not put that shop there, that kind of stuff. So these are the kinds of things that people are doing in Plant Wisely. On the transport planning side, and this is where it starts getting a little bit crazy. So that's a road volumes displayed on a map. And then in the middle, we've got the public transport network, really just showing what is where. Cycle networks are starting to become a thing that people care about because we've got some customers that are looking at how they can plan better for active transport. And in the top, future transport infrastructure. So that is, there might be projects that are planned or they're in construction. It's important to know when those things come online so you can make your decisions kind of with the best available knowledge. So these are all, and by the way, these are all real things in PlanWise. These are just screenshots out of the application that I stole from our marketing website. All right. So PlanWise is best at dynamic visualizations. And so that's to kind of say that when planners use Plan Wisely, they're not just looking at static images, they're able to toggle on and off all sorts of different things. And so for this particular view, these transport model outputs, they're able to select 3 transport modes, 24 date and time scenarios, 8 trip purpose categories, 4 demographics categories. So any combination of all of those things, if you want to do the math, it's about 7 million. So there's a lot there. And so my next question is, isn't this very data heavy? Yes, it's obscenely data heavy. So in less than a second, we select 33,000 kind of graphical features, join on 400,000 data rows, and then sum according to whatever those parameters were. So there's a lot of horsepower behind the scenes, and we're not going to talk about this. This is just to acknowledge, wait a second, isn't there like craziness happening? Yes. Okay, so in short, Plan Wisely is explorable data-heavy visualizations for government and private sector planners to understand people and places. All right. So to talk a little bit about, if I move my mouse, does it actually work on the screen? No, nothing works. All right, cool. So hang on. No, nothing works. All right, great. Really? Hey, all right, cool. Yeah, thank you. All right, great. So Plan Wisely, even though it's a little bit crowded from a data perspective, it's pretty simple conceptually. So on the left-hand side, we're choosing what we want to look at and choosing the parameters that are going to feed into our visualization. We've got a map in the middle. And if you want to click on something in the map, then we'll show some additional information in this right-hand sidebar. That's the general shape of it. So what's actually in this? So we have to start encoding all of this somehow. So we've got the UI components, the formatters. I'm not sure if you can see this, but like how many decimal points does the percentage sign have on the legend? Things like that feel like they should just work. And the business people say, can't you just all the time? But we have to encode this somehow into our stuff. The map style itself, we have to know the map definition, how we're going to interpolate the color scheme, which color scheme we're using, line thicknesses. On the charts, chart type, again, the value formatting, the labels for like the chart axes. How do we put that stuff? And then for the queries themselves, how do you fetch the map data that we're going to put onto the map? And also, how do you fetch the chart data for each of those charts and put that onto the map? There's a lot going on behind the scenes. And so for every one of our 250 plus visualizations, we have to map these set of choices that the user can make into these elements that we just talked about on the last slide. So I think you can start to understand the problem. We want to do a lot of advanced visualizations so that we can get lots of customers and we can get lots of revenue business. Yeah, that's it. And so the problem is, if we have a lot of advanced visualizations, we could potentially have a lot of costs and a lot of time to create those and to maintain those. And so all of that great money that we just got, yeah, is not there anymore. So we need to build these advanced visualizations that are high quality, so that people want to use this thing, and also low cost, so we don't go out of business and make a profit. And in case it wasn't clear enough already, profit is kind of the main thing here. Yeah, that's yeah. Well, I mean, this is why I have a job, and it's important for us to be profitable so that we can hire new people and do interesting things. So this is a lot of, and we'll come back to this a couple of times. Kind of this awkward part of the economics that I don't think we talk about enough in it. Well, it certainly didn't talk about enough when I was at uni. All right, so building this visualization system. How do we do it? I'm going to introduce a little bit of a framework here. There's a nice little visual framework for how you can build out platforms. I'm just stealing it essentially from Alex Komorowski. There's a link there in the top. He did this amazing like 200 slide thing called gardening platforms. But he uses this like matchstick type diagram where these orange dots are the pieces of value that we'd like to somehow figure out to go and capture. And then the stems of the matchsticks is how much effort it would be. So if you line these up the whole way, that's a lot of effort to get to the top of that part. And so we're software people. We know how to do this. We reduce the effort required to get to each of these by building the shared components, like the decorators, that kind of stuff. We're reducing our effort. So what does that look like in Plan Wisely? We've got a map colored by the population, and we want to get to a map colored by income, and there's a table for the age breakdown or something. These are the kinds of requirements that we get. Let's say we've got the web application, the visualizations database, and the data server ready to go. We're not going to talk about that. So we'll make a colored map component, add that in. We'll make a table and we'll add that in. Great. Good so far. Okay, more requirements. All right. I'm seeing a pattern. Colored map with controls for the subgroups, charts for select areas. Great, let's do it. So we'll extend the colored map. We'll add this query module on top. We'll add the button group to control it, and then a bar chart on top of that. Great. Okay, easy. No, give us something hard to do. Oh, okay. So now we want to do this network map with controls. We're going to have charts for the selected link, custom styling, and then drop downs because there are too many options for the button group now. That's actually how it went. So we have to build a new network map component. We'll reuse our query module, new drop downs, the styling controls. Yeah, that's a thing. Then we'll reuse the table from before. Oh, okay. The bar chart, something's not working here. It's not fitting together. So we've got a type mismatch between a bar chart and how we want to use it. It's because the table kind of needs to plug into something, and then right at the top here, we've got our bar chart wants to plug into the table. No can do. All right, this is where we need to start looking at some code stuff. So we don't use Haskell for this part of our application. We're actually using a thing called Elm. And Elm bills itself as a delightful language for reliable web applications. This is what it looks like, by the way. This is just some Elm there. It's another ML family language, so it's similar to Haskell in its styling, except we don't have do notation and we don't have type classes, which is, yeah. One thing that it does have, which is really fun, is these nice records. So if you look at the conversation type I've got there, the constructor for greeting takes one argument, and that one argument is an anonymous record with a field, name, type string, and enthusiasm type int. And so it's able to just kind of conjure these record types and have these passed around. And that turns out to be really, really helpful for doing just like normal programming things. Record syntax in Haskell kind of sucks. Uh, the other thing that does that's really interesting is that partial functions are compiler errors, and so we get almost no exceptions. So unlike in Haskell, where if you accidentally use head and you don't have your warnings configured correctly and you just run into problems, Elm just doesn't have any of that. But that's also got some downsides, which means that you can't cheat ever. Like ever.
That's right.
Mm. All right. So coming back to our problem. So why not just special case that component? And the answer is really just we'd have a lot of special cases, and then the money flies away again. So that idea that if you've got the 8 Lego bricks, you've got like a billion combinations of how you can connect them. We're going to run into this same thing. We're going to have just waste all of our time. And so to avoid this combinatorial oblivion, Joel, who's one of the former tutors here, he came up with let's just do an expression language. Classic grad move. But it was good. He implemented a proof of concept in a couple of days. And this is kind of what it looks like after a little while. So it was like JSON syntax, pretty horrific. We intentionally made it non-Turing complete because we thought that was a good idea. So like we wanted to be, guaranteed termination, things like that, and that would keep our system low cost. I'm putting scare quotes around everything because it was bad. So it was untyped, and because implementing a type language, that's like years of work, so we're not going to do that. But what we found it happened is we actually evolved into having a second expression language inside our first expression language, which only applied to certain fields. And then there was magic everywhere. Like, I don't know if you can read that, but what the heck does as colon 24 hour colon min colon hour mean? I don't know. We couldn't tell it to anyone either. And the lack of the Turing completeness, the real functions, meant that we had so much code that because we were duplicating for all of the different cases. So all you can really do there is enumerate things. And so our interfaces ran into the thousands of lines, and people still weren't happy with them at all. So anyway, so this is coming back to this economics idea. We kind of have a choice of do something that we know is not going to really work that well, uh, and have something that we can use earlier, or we can kind of punt the problem and then have something that's more efficient. We had to ship something because industry. So Haskell and Elm are great at making that migrating possible because the refactoring is so powerful. But yeah, if you're paid to make software, your software problems are business problems. So we had to take this not very good option for a little while. Yeah, yeah, business. Yeah, all right. So, I mean, this is what it looked like in reality. So, customers were complaining, we were tripping over our own complexity, blowing through deadlines, and that was despite trying to avoid all of that extra effort. So, where did it go wrong? We didn't have error messages. That's probably a rookie mistake. They only worked most of the time because we didn't have like a type system to really help us. And in trying to keep the core system simple, we pushed all of the extra complexity into everyone else trying to use that core system. And so at this point, a single visualization was taking about 2 weeks to build, and it would still feel incomplete at the end. You'd be like, "Oh, can you just do that?" And I'm like, "Oh, that's like a couple of days' work. What's going on?" And it was about this point that we started finding some dangerous material. So, kind of in Brisbane Functional Programming Group, which is a industry group that meets up to talk about functional programming. Very cool. Meets once a month. I should have had a link in here. That's a mistake, but you can find it. Look up Brisbane Functional Programming Group. There was a talk. Jack Kelly was referencing this crazy MacGyver's Haskell compiler thing, and he'd done a proof of concept using an evaluation strategy using combinators, which are like an alternative implementation to lambda calculus. And about that at the same time, like Leonard Augustin, who was also working on the Haskell compiler for the last like 30 years, maybe 40 years. This is his retirement project to just re-implement GHC for funsies. Yeah, yeah, just for fun. He literally says it's just for fun, so like feature requirements not accepted. So that's great. And when we started looking, there was a fair bit of academic research about, maybe this could be possible. Maybe we could write a typed expression language. So the requirements, what do we want? We wanted some types, of course. We wanted those anonymous records from Elm because they're awesome. We wanted existential types. Elm can't do those, which is again kind of weird. So this magic print type, we've got the for all on the right-hand side. You're kind of erasing that type. You can't do that in Elm. You have to say, oh, it's this type, and that means you can't have. Essentially, you can use this to kind of make a non-homogeneous list, so lists of different types of things. And that's quite important for us for going, oh, we want multiple map layers that have different data models internally. But anyway, we didn't use type classes because we worked out that you don't need them and they're quite expensive to build. And infix operators, YOLO, just out the front, please. So that's what we did. And that's why we've got if eq. That's how we're quality. But hey, we're paying people to use this. That's all good. And this is where we landed. Oh gosh, yeah. Building a compiler. I'm not going to go too much into a lot of this. This is the standard compiler shape, but I do want to shout out to Joel, who did a lot of the legwork here, building the kind of the first version of all of this stuff. He went on to do some academic stuff. We replaced him with someone who's doing dependent type research. That's Donovan, and he kind of knocked things into a better shape for us and provides some guidance. I essentially saying this because there's really smart people on the team. And I think most people wouldn't even think about doing this because like you have to find people who go like, you know what, I think I understand the bits and pieces for this. That's pretty hard. I guess the weird parts of our compiler to highlight are this: we're using combinators for the code gen, and then the we also want to be able to kind of generate code based off the map talk into Elm, and that becomes really important, and we'll talk about that a bit later. So the system as a whole, and this is a very busy slide, apologies. But we start with visualization. We compile it into some runtime representation. We use libraries. This tool has libraries. That's really important as well. And then we can evaluate that in the maptalk runtime using those Elm types and decode functions that we generated from our maptalk. And so that's also quite important. And I think I'll do a demo later and just show you why that's really important. And then when it comes to our application, all we're doing is just implementing the Elm types that were generated from the map talk. Great. And this is using all of that. So crazy amounts of complexity behind the scenes, and just looks like, hey, this is a cool user interface, and it kind of works as we want. So what about maintenance and tests? Yeah. I don't know if you've covered this before, but this idea that your types are essentially like proofs of logical statements. And this is a super powerful tool you can use in other languages as long as they have somewhat of a type system. And so there's this idea of like our programs are kind of like proof. So if they type check and you've structured your types in a certain way, then you have some proofs of things. This is an example down the side. So that this head, this is the partial head. It's a lie. Like behind the scenes, it's essentially implemented like this. Uh, this is annoying to use. So you have to pattern match on your maybes whenever you do anything. This one over here is kind of better to use, but you have to have had the proof that you have a non-empty list. And like I'm using proof here. It it feels a bit disingenuous to me as a programmer because I'm like, well, it's what do you mean it's a proof? It's just like a data type that has the value in it and then the rest. And so of course you can always get the value out. That's pretty straightforward stuff. All right. So proofs in MacTalk. So how might we structure our application so that we have a proof that our visualization is valid? That was the goal that we started with. This is a naive approach. Can anyone see something that's wrong with this already? Yeah, pattern matching on the just. Yeah, pretty tricky one there. And so like the type signature is lying, of course. You can't write something that's meaningful here. So let's tweak this. So we'll make this into a maybe string. So like that's our state towards a maybe visualization. And this isn't very helpful. So like I will give you a maybe $10. Yeah, and you're like, oh, okay, all right. It'll be a nothing inside, don't worry. Uh, like it's safe, but it's pointless. But I think as well, you kind of left with this niggling question of can we really implement the component functions from this definition? And I think the answer is just no. Like we don't have enough information from these types to be able to say, yeah, we can write a function. And these functions end up being quite trivial. We're just going, grab this thing from here, grab this thing from there. There's not much parsing happening at this point because all of the parsing had to happen before so that we've had our guarantee that this is a valid visualization. All right. So this is getting closer to how we actually spell all this out. So we structure all of the capabilities of our interface engine kind of using this constructivist approach. So you can't just specify a color scheme using the string blues. You have to provide the value blues from our color scheme type. And so we can build up all of our visualizations, and it's kind of trivial to go, yep, we have a type, we know about this, off it goes. And so if we have a valid like if compiler says yes, then we have a valid visualization. We can send it through to production, off we go, which is great. That's an awesome property of the system to have. So when it comes to testing our system, remember the Elm, the maptalk generates the Elm. And so because of the Elm compiler, we have a proof that our Elm implements the maptalk components. Because of the maptalk compiler, we have a proof that we have a valid visualization. And then we're just kind of clicking around and playing with the data that we have. And that's, we just call that data QA anyway, because that's when we're checking that the internal data sets, everything looks right. Like to the people loading this, They don't care about all this other work that we've done. They just want to see that their data set looks about right and there's not crazy values in there. And then if something happens to look wrong with the visualization, they just tell us, we fix it. It works for all other uses of that value. So how did it go? So this was our chart from before, and obviously we want to be on that high chart, right? Like that's where the money is. That low one, we're going to be spending a lot and taking a long time. This is our rate of visualization imports over time. And so you can see when MapTalk comes online, woo, hockey stick. It was pretty great. So we used to be averaging about one per fortnight. We're now averaging about 8 per week. And we've got 250 visualizations using about 50 components imported in the last year, which is pretty cool. The other part that is an excellent flex is the visualization updates. Because we're using proofs here, we have really good confidence that these things are going to work if they do. So half of our visualizations have been updated in the last 2 months and 90% in the last 4 months. And the last 10% is probably like abandonware. Who cares? Yeah. Awesome. So I guess the takeaways, designing the systems to support these automatic verification significantly reduces the costs, profits, business. And type checking can be simple, but remarkably effective proof system. The simple part's hard to stress. If you want to do anything interesting, go look at dependent types and do a PhD or something. That's where it's at the moment. The academic FP stuff can be super useful in industry. Actually, it was Donovan who was working on the compiler at one point, used to say that, half of these wild industry things are just applying the academic stuff from like 30 years ago, and it's not wrong. And finally, hopefully you take away that the planwisely team is working on some cool stuff, which is great. All right, questions?
Speaker, I'll just tell us that you control the room, so just
Yeah, great.
You guys know how to answer that question still.
Excellent.
Right.
Yeah, go for it. What's the number, Lyndon? Like,
12.
yeah, 12 on the team, maybe like 8 software developers or something. Yeah. So we didn't have the option to be like, yeah, we'll just throw people at this problem. So we had to turn our brains on and get busy. Yeah. Yeah, go for it. Nope.
Is your flaggers not against it at all?
So, I mean, one of the fun things, so we're using Alex, and so we have a real grammar. And so once you wrap your head around the Alex framework, you can extend the language. But it's all private, commercially sensitive-ish. So there'll be, I've skipped over a few details. Yeah. Yeah. Yeah.
If you were looking at pick up someone, so like who's just graduated or something,
Yep.
kind of like, because I guess there's only one functional programming. What other like skills would you look for? Like any like math subjects you recommend? Things that priority to you, or is it just more?
Not so, the best thing you can do is just to get seat time with Haskell. So try and build your own projects and try and do stuff, and then because when it comes to the interview, we'll sit down with whoever we're interviewing and kind of look at some code and ask questions about what's going on here. How's it working? How would you do this differently? What are some of the design decisions that they've made? And you can talk about that stuff because you've been writing Haskell for a while. Then you'll do awesome. But I think like it's not really a dirty secret, but like when we're screening candidates, we're often looking at the side projects more than the courses because like we care that you can build stuff, not that you can pass your courses. Because it's people can pass courses, that's fine, but they might have been spoon-fed a lot of the stuff, and we want people to be independent and passionate about building stuff. And so I think that's the shape of things. Try and find some interesting projects and have a go, scratch your own itch type of a thing. Yeah.
Anything else? Okay, well, absent of any more questions, let's thank the speaker again.
Oh, hang on. Well, I thought I might show you what it looks like.
Oh.
Does this sound good? All right. All right. So we're still okay, cool. That's running. So I was inspired by Paul's stuff. I watched some lectures and I thought, you know what? Let's do some live coding. What can go wrong? So is that working? Yeah, something like that. Yeah. All right, so I've got a demographics and family composition. So this is what it looks like. So I could do this on production. I'm not going to do this on production.
Once you put a time, you change it.
Well, I want to be able to change it and kind of show off what it looks like to change it because I think it's one thing to kind of see what this is and another thing to be like, wow, you've made really difficult stuff trivial. And so I want to show what that looks like. So this is like the examples that we have where, we can just change stuff. Let's look at a different geography level. Off we go. Family composition type. We care about one parent families with children. Sure. Where do they live? These are the kinds of things. So this is what Plan Wisely does. And this particular uh, interface is defined using this. So we have to have metadata. So these domains, we didn't really talk too much about them, but uh, they're essentially like syntax sugar for not having to write case statements all the time. Because we'd just be writing trivial, when you see this, return that. When you see this, return that. Like it's kind of boring stuff. Put them all on the same line, profit. Okay, and so there's a lot here. We're not really going to be able to dig into it. The vars that we saw at the start, they're kind of pointers into this state, which is managed by the runtime, but they're typed, right? So they have a name, and we remember that, and they have a type, and we remember that. And so the selected, so that it ends up being back to functional again, where we run our thing, we apply the actions, and we get a new value. So we just have this big event loop, where we mutate the thing in the middle, but we've just kind of hidden that explicit structuring of the state type, so it's easy to farm out work to other people. Okay, so I thought I might try and add a new component. There's no heading, no description. And for the content, let's go bear planwisely.bear icon. Cool. All right, so I can save that and let's go have a look. So we're trying. Oh, hang on. No, that's a real error. Okay, good. There we go. That would have been like a few hours of work potentially if we made too many changes in the old system. So now, okay, great. It can't find our planwisely bear icon, which, that makes sense. So I'll jump into my planwisely library file. So this is the contract that we have with our application for what we need to have. So if I find, where's the icon? Let's chuck in a bear icon here. Yeah, it doesn't need any data. That's fine. So I can run that again. Desugaring, type checking. Hey, cool. All right, great. Done. Compiled, happy. We have a valid visualization. Next thing to check, do we have a valid plan wisely? Oh, okay, that was from running some other things. Oh, no. Okay. This is super cool. So we've just changed our map-talk library, extended it to have the functionality that we wanted, and now our Elm compiler is going like, whoa, 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 you've forgotten some things. You can't actually, this thing that you've tried to use doesn't exist, or you've tried to use it and you're using it wrong, which is awesome. So I can go, oh gosh, am I gonna have to show people this file? Please no. Okay, I know what the problem is anyway. It's the always problem one. Oh man, I'm gonna have to add them to all of these. Okay, fine. Bear icon, normal treatment. This is what we get for making shortcuts in other places. Where else are the issues? No. Oh, hang on, my Elm stuff is not happy. All right, great. So to the next issue, bear icon. No, yeah. Didn't I call it bear icon? Yeah, I did call it bear icon. Thank you. On the money. View inner, great. Let's do our decal bear icon to a HTML.text, and then what's the Unicode for bear? Gosh, and next question is how do you do that in, you know what? I'm just going to copy this and we'll see if this works. Yeah, awesome, great. And then, okay, that's happy. Yeah, let's see if Elm is happy. Elm is happy. And then back over to Plan Wisely. This is updated in the background. I can import the product for out JSON, and this is probably going to be incredibly small and in the top corner. But check it out.
Oh, shoot, sure.
Shift it, boom.
Go.
So this is awesome. Like it's all the things that used to be really hard and now quite easy, and that lines up really well with the shape of what we're doing. And we've used just functional programming wizardry behind the scenes. Impossible to explain to customers. How do you do this? Yes, we do it. Yeah, question. Yeah, so that's what Elm is. So Elm is it actually started around the same time or like predates React a little bit. It's still faster than React and generates smaller binaries. The whole thing runs on JavaScript. So the content just before when we're talking about applying functional programming concepts to Python, they did the same thing to JavaScript. And so like you can literally find here's the A2, which is apply the curried function with the two thing. Like that's how that stuff works. You can look at the contents, which is super cool. Yeah.
Go fair now. Go use the functional programming in real life. See you guys at the exam.
Awesome.
I'll be there in spirit. We'll see my Patronus.
Stop share.